Hi class. Chapter 3 is all about calculations with chemical formulas. It's about moles, it's about percent composition. In other words, so far what you have learned it is how to write formulas, how to write balanced chemical equations. So you have learned more theoretical, more qualitative aspects of chemistry. This particular chapter probably is going to be the first one where you're going to start encountering more mathematical, math-based problems, the do's and don'ts of what goes on in case of a chemical reaction, how you can set that, what's theoretical yield, how one can determine a percent yield for a given reaction, and things of that nature. So, continuing on, what I want to first talk about is atomic mass unit. Atomic mass unit, commonly referred to as AMU, essentially is a relative atomic mass. Recall from chapter 2 where we first discussed the Dalton's atomic theory, and I told you that essentially for Dalton the mass of an atom was really important, and what he suggested was that the mass of an atom, or atomic mass in other words, is what characterizes an element, and that of course later on we found was not true. In fact, one particular element can have different masses, because when it comes to mass we really are looking at contributions made from both the protons as well as the neutrons at the center nucleus. On the other hand, now we and of course we know that it's basically the atomic number which characterizes an element. But anyway, the reason why atomic mass was brought into place was because in simple words, you can say, just for simplicity, just for clarity, imagine how difficult it would be if you were to remember that the mass of hydrogen is 1.66 times 10 to the negative 27 kilograms. So while mass was taken in kilograms, it was important to simply have a relative scale, have a relative atomic mass scale, where they defined the meaning of 1 AMU, and then every element was measured with respect to that 1 AMU. And this was done basically to answer a problem point, because at any given point of time we could not isolate a single individual atom. We couldn't do that, and so we only were able to define the masses of atoms relative to each other. So in the beginning it was started essentially keeping hydrogen as a scale, and experimentally it was calculated that a gram of hydrogen basically required approximately 8 grams of oxygen. And so if you wanted to calculate the grams of oxygen that will be required for the formation of water, since it's H2O, we can say twice the 1 gram of hydrogen will require twice the 7.9367 grams, which in turn means close to about 16 grams of oxygen relative to hydrogen. So in that sense, having a scale, the concept of AMU came in pretty handy, because now all of a sudden we were looking at the really microscopic level atom at a much more macroscopic scale. So like I said, Dalton provided the hydrogen base scale, but then later on it was changed to an oxygen base scale, which was then later on changed, I think around 1961 or so, to a carbon-based scale, which we don't really call it an AMU, but more like a unified AMU. And the most modern definition of an AMU is that it is the size of 1/12 the mass of a C12. And it turns out that that number comes out to be 1.66 times 10 to the power of negative 27 kilograms. So it really is a very, very small number, but just for reference, I'm giving you that. And now the chosen standard is taken to be the C12, and both the measurements of mole, as we will see in the next couple slides, as well as the concept of AMU revolves around carbon 12, specifically the 12 isotope, the C12 isotope of carbon. Just to give you a flavor of how these masses are measured, they're done on an instrument called as mass spectrometer, which essentially measures masses of different isotopes. The requirement is essentially that your species that are going through must be charged, and hence irradiation with some kind of an ionizer like an X-ray or something needs to be done, and then it's allowed to fall by varying the voltage and by looking at the various speeds with which they move, or the deflection that is made. The masses are measured. Something you will learn, perhaps those of you who will be taking organic 1, you would learn more details of how that can be done for in order for you to be able to determine the molecular mass of an organic compound. But realize, when we are looking at the unit of atomic mass, we call that AMU, even though in reality this has been discontinued, and most people would just use the letter U for unified AMU, or perhaps Dalton, DA. But so let me just write that, Dalton, and U for unified AMU. But even now, if we are writing AMU, it is essentially keeping in mind what the meaning of unified is. All right, let's see if we can actually take a step forward and be able to determine the molecular masses. So I want to go over what are called as atomic masses and molecular masses. Of course, we have looked at atomic masses in the last chapter. Essentially, the sum of those atomic masses put together, keeping in mind the number of atoms of each kind that are making up that molecule. This will give you the molecular mass. Realize the word molecular is specific for the molecular compounds or covalent compounds only. So you can use either the word molecular mass and just very specifically say that this is for covalent compounds. That means it will have all nonmetals. So if you were to determine the molecular mass of, let's say, water, you would say there are two hydrogens, and for the sake of simplicity, I'm just going to use 1 as the atomic mass for hydrogen. You can use the number given in the periodic table, but my purpose here is basically to show you how to set these equations. You have 1 oxygen in H2O, so 1 times 16 is going to give you 2 plus 16, which is 18 AMU, or 18 Daltons, or 18 U is what you are going to get for the molecular mass. Likewise, if you were to do that for C2H4O2, you would say 2 times 12 plus 4 times 1 plus 2 times 16, which is going to be 24 plus 4 plus 32. So that will come out to be 60 AMU as your final answer. And again, we are calling this molecular mass because it is for a molecular compound. Very similar to that is what is called as formula mass. In this case, we say that formula mass is the sum of the atomic masses of all the atoms in a formula unit. So in cases where you essentially have the capability to determine for an ionic compound, you would be able to say that for the ionic compound, provided the ratio is the simplest ratio, the formula mass and the molecular mass is going to be the exact same thing. Covalent compounds, like I said in the previous slide, essentially will have just the molecular mass for them. So if we have to calculate the formula mass for sodium chloride NaCl, realize we have only one sodium, so 1 times 23 plus Cl is 1 times 35.5, and that will add up to 58.5 EMU again. And likewise, you can do the same thing for magnesium carbonate, getting the masses of magnesium, carbon, and oxygen from the periodic table, multiplying them by the requisite number of atoms, and then just adding all of those together to determine the formula mass for this particular compound. The question here is calculate the molecular mass or formula mass of each of the following to 3 significant figures. So in this case, since it's CHCl3, all of those are nonmetals, we really are determining the molecular mass. So again, I'm going to keep it simple. 12 plus 1 plus 3 times 35.5, and that's going to give you your total number will come out to be 119.5, and so you can report that as significant, 3 significant figures as 120 AMU. Alternatively, if you had to do that for Fe2SO4 thrice, that means you would be doing that as a formula mass. So twice the mass of iron plus 3 times the mass of sulfur plus 12 times the mass of oxygen, and you will have your answer that way. Let's go forward. You can probably work on it in your own time. I want to get started on what Avogadro's number is and the concept of a mole. So if you think about Avogadro's number or a mole, what does a mole mean? Well, it's nothing but a number. Just the way we say that a pair of socks, and in our head we automatically know that we are talking about two socks. If I say a couple, again you're thinking about 2 people. If I use the word dozen, you know we are referring to 12 dozen mangoes, dozen bananas, whatever the case may be. Likewise, score means 20. So if we talk about a mole, a number that should ring in your head is 6.02 times 10 to the 23 particles or socks or desks or shirts or whatever it is that we are referring to. So a mole of a substance is the quantity that contains as many molecules or atoms or particles or formula units or whatever it is that you want it to contain, as there are in exactly 12 grams of the C12 isotope. So again, going back to what I was telling you earlier, the standard now is the C12, and we compare everything with respect to that C12 isotope of carbon. Now, in terms of how much 1 mole would weigh, it would be exactly same. So let me write that somewhere. 1 mole weighs exactly same as atomic mass in grams per mole numerically, and molecular mass in grams per mole as well. That means the numerical value that you get for atomic mass or molecular mass is what you're going to see as a molar mass as well, molar mass. And if it's for an element, then you're going to talk about the atomic mass if it's a monoatomic element. On the other hand, if it's a molecule or a compound, which will obviously contain molecules, then you're going to say that it's going to be the molecular mass. But either way, it's the units that are different. The units for molar mass are grams per mole, but numerically it is the same value. So, in that sense, a molar mass